So welcome to Math 150, multivariable calculus. This is the last lecture of the semester. And what I want to do is I want to just continue with applications. And I want to talk about what can you do with the math that we've done? What would you see if you continue in mathematics? I'm going to talk a little bit about discrete mathematics, a little bit about game theory, a little bit about analysis, a little bit about statistics. And of course, since this is a multivariable calculus class, I will make sure that we emphasize some of the things we've done in multivariable calculus. All right, cultural extra credit. What is the title inspired by? From M&Ms to mathematics, or how I learned to answer questions and help my kids love math. Dr. Strangelove. Excellent. All right, so this is inspired by a talk I gave many years ago at the 110th anniversary of a Association of Massachusetts Math Teachers. And the point I really wanted to address is the world is rapidly changing. And I did not know at the time just how different things would be in 10 more years from when I gave that talk, in terms of just how things have moved and migrated since we began. What are we teaching you and why? So I am old enough that when I first came at Williams, they did not have Math 130, 140, or 150. Back then it was Math 103, 104, and 105. And I still remember my first TA for 103 being absolutely amazed that as a professor, I got to choose what we covered. Now, if you don't cover differentiation in 103, you're in trouble. There's certain things that you have to do, but there's a lot of freedom. And as you get older and older and older, you realize you can look up facts. When I was a kid, there really wasn't a great internet in the beginning. If you were at military installation, sure. If you had a big company, there was an internal system, sure. We didn't have home computers connected to the internet. We didn't have cell phones. We didn't have all this access. We had these things called books and libraries that you would go to. I spent 4 years in Yale working in microfilm, microfiche. And so it was hard to get information. You really had to know things. Nowadays, because things can be obtained so easily, you don't have to learn all these facts. You have to know how to learn. And you have to learn how to search so that, okay, if I need something, I can quickly go online, read a quick paper, read a quick something. Okay, we never did radial integration when I took Calc 2. It's just 1/2 of theta squared d theta. I said, oh, okay, it's triangles, got it. Now I can do it. Have you seen the matrix, just downloading the extra skill set? I know cultural extra credit. What does Neo first learn? That he is then tested with?
Hand combat.
Which one?
Kung Fu.
It might be Kung Fu. It's either Kung Fu or Jiu-Jitsu. I can't remember. So you can check and see if you get the cultural extra credit. So you can just get these skills now. So what do I want to teach you? I want to teach you more about how to think about problems. So, a couple of pieces of advice. Ask questions. Look at what's already been done and see, can I push this forward? Can I ask something new? Can I remove a condition? What is this related to? Gather data. It is amazing how much data we can collect now. And when you have all this data, the hope is that you can figure out and find relationships. And you can make conjectures and hopefully even prove them. I like to use games to excite and interest people. This is just more of a presentation choice. But there's a lot of wonderful game theory questions that have led to incredible developments in mathematics. A lot of probability was developed because people were interested in gambling. And you're trying to calculate the odds. All right, so these slides were made when my son was 8 and my daughter was 6. They're a little bit older now. And so the inspiration for all of this is the MandMGame. So when my son was 4 and my daughter were 2, I would often pick them up early from childcare and we would do various things. And one day my son asked me, and he's 4, if you're born on the same day as someone, will you die on the same day? I thought that was a really good question for a 4-year-old. And so how do you explain randomness to a 4-year-old? Well, one possibility that I considered is, remember how mom's an identical twin? Yeah, look, mommy's still alive. Okay, that's not a good way to explain randomness to a 4-year-old, right? Not a good choice. How can I come up with a way that would work? And so we created the MandMGame. And so the 2 rules are everybody starts off with K M&Ms. We did 5. We had those little small bags. And then you all toss a fair coin at the same time. And if you get a head, you eat your M&M. And if you get a tail, you don't. It's almost a decade later. My daughter still remembers the game when she got 5 straight heads and got to eat all of her M&Ms as fast as possible. Now, when you look at the picture, so you can see the Kayla, the Cam, and the dad column, what do you notice about this?
Yeah, that's a different column.
Yeah, so what do you notice in particular? Little kids may care about things that big kids don't, yes.
That they're more or less color-coded.
Yeah, so Kayla really wanted the blue M&Ms, and she got all the blue M&Ms, and then we didn't have 5 blues, so she had to take a yellow. What about Cameron? What did Cameron choose to do?
His color scheme that were all on color.
But be more specific. Well, what did he do? He had a pattern. Cam chose to have a pattern. Do you think this matters at all in the game? Yeah, I got whatever was left over. I made the best pattern I could with what was left. I probably should have done your orange, green, black or brown, green and orange, and done a pattern like that. All right. So what are some questions you might ask about this game? So this is the most important part of the lecture. Give me some questions.
Was it a fair coin?
Well, okay, we'll assume it's a fair coin. So what might I want to know questions about the game as the game evolves? Yes.
On average, how many rounds does it take for someone to
Good. On average, how many rounds does it take for someone to
yield that?
eat all the M&Ms equivalently to die? So I was explaining this a year or so later at a birthday party for one of my daughter's friends, and the grandmother really liked this, and she does children's stories, and she wanted to know, could we, instead of having people die, could we have something else? You know, this is not going to work well in the children's story. So one is, how many rounds does it take on average before a person runs out of M&Ms? What else could you ask?
Like how does the order affect?
What do you mean by order?
Like who flips the coin first?
We all flip simultaneously, all same time. So remember, the original question is, if you're born on the same day, will you die on the same day? So what probability might we want to calculate? Yes.
Given that you have n number of players, what's the likelihood that someone dies on the same day?
Sure. What's the probability of a tie? Or 2 people dying at the same time, if we do just 2 people initially. Now, what if the coin wasn't fair? If the probability gets closer and closer to 100%, what do you think the probability of a tie becomes?
Closer and closer to 100%.
Yeah, closer and closer to 100%. So you can start to ask, what happens if you have a biased coin? What happens if you have more people? How likely is a tie as a function of k? How long until? There's lots of questions you can ask. The challenge then becomes, which ones can you actually answer? So let's gather some data. So in the pre-pandemic response era, we would actually have coins and M&Ms and actually play the game for real. I will try to remember to bring M&Ms when we go to Lec36, so that if people want to put M&Ms on or play, they can do so. Here's a plot of the first couple of values. So with 1 M&M and 2 plays, it's a 33% chance of a tie, 19% with 2, 14 with 3, 10% with 4. Do you want more or less data? Or do you have enough data to make your predictions for what happens in the future? More data, less data, or you're happy?
I mean, I guess theoretically, more data is always helpful.
More data is usually good. So let's do more data. Let's go up to 110. So I gave this at the 110th anniversary, and then I asked, where do you think we'll be in the next 110? So at 110, it looks like it's around maybe 0.3, somewhere between 0.2 and 0.3. So what do you think is going to happen at 220? Where do you think it's going to be? What do you think it might converge to? Any thoughts? So when we did the German tank problem, we saw that the slope was 1 + 1 over k. And we even saw that when we looked at the plots of the best fit slopes. And so for there, as k went to infinity, it converged to 1. What do you think this might converge to as k goes to infinity? So fair coin, 2 people each start with k M&Ms. Yes. So it might go all the way to 0. That becomes extremely unlikely that they're going to end at exactly the same time. They might end up very close. They might end up within, if we have 1 million M&Ms, they might die within 3 days of each other. So cultural extra credit, what day had 3 US presidents die?
July 4th.
July 4th. And who are they?
Thomas Jefferson,
Yes,
his arch enemy,
at times.
at times, they're both really. George Washington,
Not George Washington.
Monroe,
Monroe was one. Who died with Jefferson? It was the 50th anniversary of the signing of the Declaration of Independence. Not Madison. First New Englander to ascend to the presidency. No, he is the second New Englander to ascend to the presidency. John Adams, right? It's much safer to just say John Adams, because that gives you 2 possibilities. And I could say be more specific. So when you look at this, it's not at all clear, is it going to 0 or is it maybe going to like 0.01? It's really tough to tell. So does anybody want to guess what it might be around 220? Or is there something we could do that might make the data a little bit easier to look at? What could we do to the data? Take the log, right? This is one of your go-tos after taking a class with Miller, right? So what did you learn? I learned to take the log, right? How many of you learned logarithms in high school? How many of you were told why we care about logarithms in high school? Hey, it's a unit in the course, we need to do logarithms. One reason we care about logarithms is we can look at data that spans numerous orders of magnitude. If we have a proton and a galaxy, the number of orders of magnitude is amazing. And to talk about them in the same plot is a miracle. One literally dwarfs the other. Logarithms allow us to talk about that. Logarithms also allow us to see relationships that are hard. We are very good at identifying straight lines. I think you can look around this classroom and see numerous examples of straight lines without too much trouble. So let's take a logarithm. And so if we take a logarithm, we get the following. Does this look like a straight line? So we have a portable line identification system, high technology. And so we will use this to empirically determine if this is a line. What do you think? Not bad. It definitely looks like it could be a line. We want something a little bit better though than professor holding up giant rod to projection screen. So we use the method of least squares. We talked about linear regression earlier, and we find the best fit straight line. Does this look like a good line? Does it look like a good fit? Any parts that concern you? Yes? Yeah. Yeah, so it seems like the line starts off a little bit low, and then it becomes a little bit high after a while. So where do you think the line is having the most difficulty? I wouldn't say is it. Okay, so yeah, so in the beginning. So it could take a while for things to settle down to the relationship. Imagine your company like Amazon. You might have those years in the beginning when Amazon is selling basically like just books and whatnot, and it takes a while before it finally hits that place where now it starts to move to dominance, and you maybe not now start having exponential growth each year. So you could have different phases of the company. And if you try to use all the data, well, the data of who you were in the beginning is no longer relevant as I go further down. I've now hit new limiting behavior. What should we do?
Analyze that respectively.
So be specific, tell me what I should do. So here I looked at the data of the first 110 and used this to find the best fit line. What could I do instead?
cast it out as an outlier.
Okay, so be specific. What should I do?
With the error.
I'm sorry, nope,
Like take the data, if like what you care about is 220,
right?
then you can look whatever, take the data from 50 to. like,
Good. So throw away the stuff in the beginning where it's fluctuating, and then from like 50 onward, let's look at what's going on there. So if I use this best fit line, I get a prediction of a tie when k is 220 is about 0.01274. The correct answer is 0.01374. The amount that it's off by is not a terrible amount. Percentage-wise, it's a decent amount, though. It's ballpark, but it's a large ballpark. I'm not getting 50%, I'm not getting 5%, but I'm still off by a decent amount. And so the question is, can we do a little bit better? Well, remember, we have a discrete process. And so with the discrete process, maybe those first few tosses in the beginning, it's not settled down yet. And so now let's look at just looking at the last 50. And so I actually chose to do 50 as well. Can you tell if that's a good fit or not? Let me zoom in. Yeah, this seems like something you would see in like a chemistry class. Those perfect lines going through the little molecules. Does that look like a good fit? I mean, to me, this is one of the powers, is that you have these incredibly complicated relationships. And if you look at them the right way, the lower order terms become insignificant. You can capture the main term effects and really see what's going on. This is a phenomenal fit. Let's see how well it does. So I calculate 0.01344 when k equals 220. The actual answer is 0.01347. The amount that I'm off by is insignificant. So this is, again, the power of linear regression. This is the power of taking logarithms, that all of a sudden you can sniff out these relationships. All right, so we've done the geometric hoops problem. So I'm going to go through this part quickly, right? We've done these slides. Yeah, okay. You learn as a professor that if you make slides, reuse them. So we'll do Bird and Magic Johnson. So Bird gets a basket with probability P, Magic with probability Q. X is the probability Bird wins. What is X? So we calculated this. And what we did is we broke it up into the probability Bird wins on his first shot, second shot, third shot, and so on. They're all independent. So the probability Bird wins is the sum. And we get X is equal to P times 1 plus R squared, and so on, where R is 1 minus P times 1 minus Q. So we get a nice geometric series. So if we knew the geometric series formula, we would be done. But we can use this to prove the geometric series formula. And the way we can do this is, the following. Imagine Bird wins. So he could get his first basket, which happens with probability P, or he misses probability 1 minus P times 1 minus Q, because Magic has to miss as well. And now it's like the game just reset. The first toss of both of them missing doesn't matter. So from this point onward, the probability Bird wins is just X. And what we've done is we've gone from an infinite sum to a finite sum. An infinite sum should scare you. So I will not ask who says to infinity and beyond. I'll choose the beyond. I'd like to go beyond the infinite sum and make it finite. I will ask instead, who is the father of who says to infinity and beyond? Cultural extra credit. Who's at least the character who says to infinity and beyond? Buzz Lightyear. And who is Buzz Lightyear's father?
Andy.
No, Andy is not the father. Yes.
I don't remember his name. It's like the Darth Vader parody guy. Oh, Zurg.
It is Zurg. It is Zurg. Yes.
Classic Zurg.
Classic Zurg. Right. So we'll count that as the Star Wars reference for today. All right. So Zurg is the father. So I choose the beyond. Infinite sum should scare you. We had to spend a lot of time this semester dealing with how do you tell if an infinite sum even converges? All right, if it converges, then you can try to go, what does it converge to? And then does that converge to what you want it to be representing? And I actually gave you a function whose Taylor series does not converge to it. Well, over here, when we do the algebra, we get X is P over 1 minus R. So then that means the geometric formula 1 plus R squared and so on is just 1 over 1 minus R. Technically, this only works if R is between 0 and 1, because R is a probability. So you have to do a little bit of work to show that this also holds if R is a negative number. All right, so let's look at what's going on for our problem. So for the geometric series formula for the basketball problem, there's a huge power of perspective, a memoryless process. It didn't matter how we got there, it just mattered where we were. For a lot of classes, all that matters is how many points do you have in each bin. It doesn't matter how you got those points. If you play chess, you might say all that matters is the position of the pieces on the board. No, that is not true. Chess has a rule that there's a tie if a board state is repeated 3 times. So you need to know how you got there. I don't know if checkers has that rule. I am pretty sure backgammon does not have that rule. And so for backgammon, if you're playing, all you need to know is just what is the configuration of the board. You can often circumvent difficult math with a deeper understanding if you have the right way to look at things. It is hard to find the right way to look at things. The best way to do that is experience. The more times you look at problems, the bigger your knowledge database, the more likely you will see something. This is, again, baby is crying. What technique do I need to either comfort or shut up, depending on how you want to phrase it? And after a while, you start to recognize, this is I need to use integration by parts. This is the partial fractions. And you start going through all the different techniques. And so the depth of a problem is not always what you might expect. Rather than having to deal with an infinite sum, we can make it a finite sum. So let's look at what's going on in the M&M game. So here is a formula to prove the probability 2 people tie with a fair coin. So if each person has k M&Ms, what is the minimum number of tosses we need before there's a tie? K. If you start off with 10 M&Ms, you can't have a tie with everybody eating all the M&Ms after 5 tosses. So that's why n goes from k to infinity. So why is this true? Well, if they tie after n tosses, as n ranges from k to infinity, these will be mutually exclusive events. This is very similar to bird wins after 1 toss, 2 toss, 3 tosses. For it to be a tie, they both have to get an M&M ahead on their last toss. That's why we have a 1/2 and a 1/2. Now, there are k M&Ms for each, so that means each person has to get exactly k-1 heads in their first n-1 tosses. How many ways can you do that? n-1 choose k-1. And because it's a fair coin, each head or tail has probability 1/2. That's where the 1/2 to the n-1 comes from. So this is an infinite sum that will give me the probability of a tie. Everything is non-negative. It sums to a finite number between 0 and 1. I am not particularly looking forward to evaluating this. I'm not even looking forward to showing that it converges. It's not that bad though. So as a nice extra credit problem, show that this sum converges by estimating how big are the binomial coefficients, how fast is the 1/2 to the n-1 decaying, will this whole expression actually converge? It probably should, because it's physically representing a probability. It's sums of non-negative things, but show using the techniques we've studied that it converges. Just because we know it converges doesn't mean we know what it converges to. We don't necessarily have a nice number for it. And so, just to show off, I know some advanced math and physics. This is related to a hypergeometric function, special value of 2f1 kk1 1/4 for my parameters. For most of us, that should be absolutely nothing. All right, so let's try to find a way to get a nice expression. Let's think about what's going on. So this formula really came about because at each moment, 1 of 4 things can happen, and they each happen 1/4 of the time. They both eat an M&M, just Cam eats, just Kayla eats, or neither eats. And if you use that, that's what led to the analysis we had over here. Okay? Now, let's see if we can come up with a better formula. So the big lesson from the hoops game is this memoryless process idea. So, again, this is a multivariable calculus class. I want you to be able to do an integral in spherical coordinates. But in real life, when you're no longer taking an exam, what are you going to have to do? What are you going to do if somebody gives you an integral to do in spherical coordinates? Mathematica or something like that, right? So what I really want to emphasize is to help you get to the point where you can tell Mathematica what to do. This is the Deep Space Nine series premiere, where they tell the computer, analyze the last 10,000 years of data on orb experiences and whatnot. Working will take 6 hours. All right, going to the holodeck now. You need to know how to set things up and then have the computer compute. So the big idea from the hoops was the memoryless process. Think back to what we're doing here. Can you see a memoryless process here? Yes.
I suppose each coin toss is independent of the prior.
Yes. So how does this, where was the memoryless process? What was the memoryless process in the Bird-Johnson game? What allowed us to reset things? Under what circumstance? If no one wins, so if they both missed. So now take that and tell me, where's the memoryless process here?
When nobody eats them.
When nobody eats. So how many possibilities are there really? There are 4 possibilities, but effectively, how many possibilities are there?
Someone eats an M&M.
Someone eats an M&M. So how many ways are there for someone to eat an M&M?
One.
Nope. 3. And what's the probability of each?
We're not counting.
So we're not going to count neither eats, because if neither eats, just throw it away and pretend it doesn't happen. It's just 33%. So if neither eats, it's as if the toss didn't happen. So the game is now finite, because now every time you toss, at least one M&M is eaten, and there's only 2K M&Ms, so it's got to end after 2K tosses. And so now each of these events happens 1/3 of the time. I'm not going to go through and do the algebra, but if you do it carefully, you get the following formula. And you have to take into account, if they both have a head, then you lose 2 M&Ms. Otherwise, just one person loses an M&M. And so it's a nice exercise to prove that this is true. So we actually converted this to a paper that was published. So Kim and Kayla are full co-authors on this paper because they helped create the problem. And for many things, asking the right question is the hardest part of the research. Once you know what to look at, a lot of us, it's a trained monkey problem. We have skill sets and we can just work on it. And this was joint with 2 Williams students. Okay, so we have this following formula. It's not particularly pleasant. I'm not jumping for joy, but it's a finite sum. I can plug a finite sum into a computer and I can just calculate this. Okay, it would be nice to get some rough sense, if K is large, approximately what is this? All right, so let's try to find ways to just go through the calculations and actually compute things. So I love good notation. So Cam will have C M&Ms and Kayla will have K M&Ms. Why am I using C and K? Yes, they're names, right? I want to be able to quickly glance down and see what's going on. Why do we use big F for the antiderivative of little f? Because they're related. We're making it bigger, maybe in some sense. We're integrating, we're adding it up. So we go from little f to big F. For the derivative, we put a prime. It's good notation. You can just quickly glance down and see how these are all related to each other. So on each turn, there's one of 3 possibilities that can happen. If I start at CK, I can go to either C minus 1, K minus 1, C minus 1K, or CK minus 1. So let's do this in chart form. I think for the paper, I actually did take the time with a student and make a better picture than this, but this is good enough to show what's going on. We did 5 M&Ms in real life. I'm going to just do 4 because the picture's getting big enough as is. So you have a tie if you end up at the dot 0, 0. If you're going to end up at the dot 0, 0, where must have you been right before that?
1, 0, 0, 1.
No, you can't be at 1, 0, because if you're at 1, 0, Cameron wins. 1, 1. You have to be at 1, 1. So all I have to do is find what is the probability I flow to 1, 1, and then the probability of a tie is just 1/3 of that, right? So each dot has 3 ways out. And so let's go very slowly. So I start at 4, 4 with 100% of my probability. And then 1/3 of the time I go to 4, 3, 1/3 of the time to 3, 3, 1/3 of the time to 3, 4. Okay. Now let's see what happens. For 4, 3, 1/3 of the time I go to 4, 2. Since there was 1/3 of my probability at 4, 3, that means there's 1/9 probability at 4, 2. It similarly sends 1/9 total probability to 3, 2, and it sends 1/9 probability to the dot 3, 3. So I really am calculating what 4, 3 does first. I then calculate what 3, 4 does. And now the probability that I'm at 3, 3 is going to be 1/3 plus 2/9. So that'll be 5/9. And then I see where does that probability go? And 5/27 of the time I'm going to go down to 2, 2. 5/27 of the time I'm going to go to 3, 2. I have to add the 1/9, and that's going to give me my 8/27 and so on. So for the next level, I'm just going to try to make it a little bit easier to watch. I first see what happens to 4, 2, and 2, 4, where they send probabilities. And then I'll look at what happens to 3, 2, and 2, 3. And then I'll look and see what happens to 2, 2. And so again, you can just keep slowly going through and seeing how the probability falls. And now, for the next level, I first see what happens to the 4, 1. I don't really look at what happens going into the next level because I only care about the probability of a tie. Once Kayla loses an M&M, game over. And so then I look at what happens to 3, 1, and 1, 3, to 2, 1, and 1, 2. So I have 245 out of 729 as the probability that I land at 1, 1. And so just 1/3 of that will be then the probability that the game ends in a tie, or about 11%. All right, let's see if there's a cleaner way to look at this. If I started to do logic Ks, this is going to become hell to draw. So we did the Fibonacci numbers. So the Fibonacci numbers is a depth to recurrence relation with fixed coefficients. Fn plus 2 is Fn plus 1 plus Fn. We usually have F0 is 0, F1 is 1. And we have the beautiful Benet's formula, which gives you an explicit formula for the nth Fibonacci number. If I ask you what's the millionth Fibonacci number, it's really not that hard to do. You just do a lot of additions. In practice, nobody would want to do the millionth Fibonacci number. I think we talked about just, is there enough time in your college career if you can do 10-digit operations a second? No. So if that's all you did for 4 years, you wouldn't even be close. All right, why is that useful here? Well, we can view what we have as a recurrence relation. So let's let XCK be the probability of a tie if Cam has C M&Ms and Kayla has K. If Kayla or Cam have no M&Ms and the other one has an M&M, then clearly we're not going to end in a tie. So that's why XC0 is X0K is 0 if C or K is positive. If neither one of them has an M&M, X0, 0, if we make it to that state, then it's just a tie. And then here's the recurrence relation. XCK is 1/3 XC minus 1K minus 1 plus 1/3 XC minus 1K plus 1/3 XC K minus 1. You can now program this very easily in Excel or Mathematica or something like that. Now you could ask, hey, Prof, we had a nice explicit closed form expression for the Fibonacci's. We had Benet's formula. Is there something similar here? Is there a 2-dimensional generating function? Yes, there's more involved mathematics you can do. I want to just show you a little bit what's out there. But here's another example. This is a class in multivariable calculus. So here's something with 2 indices now. How do we handle this? It's much harder. But there are ways to do this. But if K is reasonable, I can just go through this by brute force. Now, the problem, of course, is we got to this by being clever. So what is the difficulty with the method of divine inspiration? Yes, you have to have it. And divine inspiration is notoriously fickle, especially on exams, where you cannot always count on being divinely inspired. So are there techniques we can learn to increase the likelihood of being divinely inspired, to increase the likelihood of seeing this? Well, we saw that there was a memoryless process, and that led us to this. What if we didn't see that there was a memoryless process? Then I claim this is the recurrence we would have had. 1/4 of the time, there's no change. 1/4 of the time, just 1/4 of the time, Cam and Kayla eat. 1/4 of the time, just Cameron eats. 1/4 of the time, just Kayla eats. So this is the more natural recurrence relation to get. What is the first thing you would want to do when you see this? So you have XCK is 1/4 XCK plus 1/4 XC minus 1K minus 1 plus yada, yada, yada. What's the first thing you would want to do?
Subtract the like term.
Subtract the like term. And then we would get 3/4 xck is 1/4 crap. Multiply both sides by 4/3, all the 1/4 become 1/3 now. And there is just simple recurrence relation for xck. If you didn't see the memoryless process, if you wrote down the harder formula, notice that we don't have to deal with this infinity. By subtracting and doing some good algebra, we now can solve xck in terms of indices whose sum is smaller. And so by recurrence, we would already know those values, and then we can get this one. So this is absolutely wonderful that we don't have to be divinely inspired to get to this. So let's do a specific example. So here's my recurrence. x00 is clearly going to be 1. So x10 equals x01 equals 0. So to find x11, the probability of a tie when they both have one M&M, we just plug those values into the recurrence, and we get it's 33%. Now let's calculate what goes on when we have two M&Ms. Well, first we know x20 is x02 is 0. We now calculate x21, which by symmetry is the same as x12. And we just put in the values into the recurrence. And now we have x21 and x12. Now to get x22, we need x11, x12, and x21. Well, we know those. We plug that in, and we get 5/27. So we can just march down and calculate all these probabilities. So, you really want to try to find easy problems and build intuition. There is a way to view this as a walk where you have 3 directions. And so this is just an advanced topic to give you a little bit of a sense of what's out there in math and physics as you go deeper. We are walking from 0, 0 to kk, where we can take steps of size 1, 0, 0, 1, or 1, 1. Think of it as we're walking in the grid in New York, and we can either go east, north, or precisely northeast. And so this is similar to a famous problem called the Catalan problem. So it's how many ways can I walk from 0, 0 to kk, going either east or north, but not both, and never crossing the main diagonal. So it turns out that these numbers, these are called the Catalan numbers, they occur in a tremendous number of places in mathematics and physics. If anybody's interested, email me for a wonderful article by Wigner, The Unreasonable Effectiveness of Mathematics, where he's a Nobel laureate in physics and just talking about, wow, it is absolutely amazing how many of these problems can be reduced to beautiful mathematics. One way of interpreting the Catalan numbers is it is the number of ways to put left and right parentheses down so that as you read, you never read more right parentheses than left. So it's a valid way of grouping things. So it's related to problems we know. I'm going to skip this one. So what I'm going to do now is just end a little bit with some data and trying to figure out what's going on from the data. So here are the probabilities of a tie for k goes from 1 to 8. So 1/3, 5/27, 11/81, 245, 21/87, and so on and so on and so on. Does anybody detect any patterns? Yes. It's decreasing. Okay. Anything else? Anything about the numbers that you see? Yes.
Well,
I'm sorry?
ditto.
Okay. They're all integers, divided by integers, which makes sense that they're rational numbers from the process. But do you notice any patterns in the numbers? Yeah.
The denominator being multiplied by 9.
Is it always by 9? So 3 to 27 is you multiply by 9. Yes, but you're close. Can you correct it?
Real odd numbers.
They're all odd numbers, but they're more than just odd numbers. More than just divisible by 3. They're all powers of 3. I'm not going to waste your time by telling you precisely what power 4, 7, 8, 2, 9, 6, 9 is, because I know you can all just do that in your head. They're all powers of 3. How many of you took an algebra class in high school where they talked to you about the need to simplify and reduce? That's sometimes bad advice, because when you simplify and reduce, it can actually hide the patterns. So if I'm looking at ratio of integers, if I remove out some common powers of 3, I might have trouble seeing what's really going on. And so over here, it turns out that the denominators are 3 to the 2k minus 1, but sometimes the numerators have factors of 3. And so if you cancel those factors of 3, it can hide the pattern a little bit. So now we're left with, we understand the denominators completely, at least conjecturally. And we have the numbers 1, 5, 33, 245, 19, 21, and so on. The 33, we didn't have 33, we had 11 out of 81. So that 11 out of 81 should really have been 33 out of 243. And then that would have helped your pattern. If it's 3 to the 2k minus 1, there's your multiplying by 9. And that's why it wasn't showing up, because I foolishly canceled. Does anybody recognize the sequence 1, 5, 33, 245, 19, 21? No, I don't either. So there's something called the internet. And you can just ask the internet. So somebody, Neil Sloan, created the online encyclopedia of integer sequences. I and many other people have contributed to it. It is just a database of all sequences of numbers that people have found. And so what you can do is you can go to the OEIS and say, hey, I've got this sequence. Can you tell me anything about it? So I asked, Calc 2 earlier today, can you give me a sequence of numbers? What sequence of integers do you think they gave me?
0, 1, 2, 3.
Almost, they didn't do the 0. So it's a great combination for your luggage. Not 1, 2, 3, 4. Nope. 1, 2, 3, 4 is close. Anybody know what movie? It's the type of combination an idiot would use for their luggage. Spaceballs.
Oh,
Another
1, 2, 3, 4, 5.
1, 2, 3, 4, 5. Great Star Wars spoof. So they gave me 1, 2, 3, 4, 5. And so the first thing it suggests is it's the positive integers. No shit. Okay. Wow. Great job. But there's 7,228 results found. There's a lot of things. Now you can start going down, and it gives you all these papers. It gives you functions. All the nth integers just okay. I mean, it's amazing how many things are known about the integers. You can keep scrolling down. Oh, here's another one. The digital sum, i.e. sum of digits of n. Okay, interesting. And again, until you get to 10, you're not going to see the difference. Go down a little bit further. Powers of primes. Okay. The non-negative integers, I like that one.
Professor,
Yes.
so do you guys favorite Mel Brooks movie?
Yes, but I will talk about that when this is no recording. So palindromes in base 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it's going to be 11, 22, 33. So the next one I particularly love, because I asked, and that was what the student was thinking of course. And she was debating between that one and this one. Numbers k such as 266 times 10 to the k plus 1 over 3 is prime. So I have some truly impressive students. I teach at Williams. It's absolutely wonderful to have students who can think of things such as 266 times 10 to the k plus 1 over 3 is a prime. And just, numbers k with this property. What do you do when you have this many possibilities? I got so many possibilities. What should I do? What could I do? Yeah. So instead of just doing 1, 2, 3, 4, 5, I could do 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's see how much that winnows things down to. I'm still at 576. Like, what is still left at this point? I scroll down a little bit. And I've got the non-negative integers. Okay, that's still surviving. Expansion of 1 minus x plus x squared over 1 minus x squared and powers of x. And it's like, oh my God. Okay, so this is still going to go 23, 24. Where does it stop? I mean, it looks like it's going on for quite a while. So, so the question is it really just the same as that? Or numbers in canonical bijection from positive integers to, so you can start keeping more and more stuff. So for us, let's put in our numbers 1, 5, 33, 245, 19 and 21. I'm trying to remember them from the screen earlier. I think it was 15, 5, 25. Does that sound right?
Looks good to me.
Yeah, it's also the same thing on the iPad right there, the dancing down at. So displaying one of one result. And so it turns out that there's a lot that's known about this. Oh, look, the first one is the number of paths from 0, 0 to n0 using steps of 1, 1, 1, 0, 1, -1. Okay, close. Lattice paths, sums of squares of coefficients of 1 plus 2x to the n. There's different formulas, coming in from lots of different things. So it turns out a lot is known about this. If I delete, the last one, still only one number. So it's really telling me there's really only one thing this can be. 4 results at this point. And so the first one is cyclic arrangements. Okay, that's not what I have. So again, it's an absolutely wonderful website that allows you the ability to get some sense of what the answer might be. And this is the 21st century. You don't need to know everything. You just need to know how to find things. Just switch back. Okay. So we go to the online encyclopedia, and it was sequence A084771. Okay. And so if you look, I just did a screenshot of the page with the different formulas for it. It actually has a generating function. It's 1 over the square root of 1 minus 10x plus 9x squared. So in some sense, this says there's hope. There's a chance of getting some kinds of maybe closed form expressions, or maybe getting some kind of asymptotic behavior for what's going on. Given that I'm not seeing a nice formula for an equals blah, I'm only seeing things like an equals a sum, an equals a sum. Okay, I don't think there's going to be a nice, clean, exact formula, but it does give an asymptotic. An is about 3 to the 2n plus 1 divided by 2 square roots of 2 pi n. Ooh, the 3 to the 2n plus 1, our denominators were 3 to the 2n minus 1, I believe. So it's going to be like a 1/9. Ooh, a square root of 2 pi n. I might be thinking maybe a Gaussian, some kind of something like that spreading out. So it's amazing just how much you can get from something like this. It starts to give you clues as to what to try to prove. And that's one of the real powers. Okay, so just to end the semester with some takeaways, always ask questions. Take what people have done and see how can you push it forward. I think we started the year by doing extended Pythagoras. What would the Pythagorean theorem look like on a sphere? This is a question you could have asked in geometry. You've all seen spheres by the time you're doing the Pythagorean formula. And you can ask, well, what would it look like on other shapes? There are often many ways to solve a problem. Different ways are going to highlight different aspects. Some ways might generalize better than others. The more you know, the more opportunities you have. Your experience is a phenomenal guide. What does this look like? And as soon as we see that there's one case where if Cam and Kayla both get a tail, nothing happens, that should remind us, wait, I've seen this with memoryless processes before. So again, I hope all of you will continue to take math and stats classes. I am always happy to chat with you about possibilities, major, don't major, whatever, but just it builds up good skill sets and it gives you a sense of what can be done. And you don't have to know how to do everything. You just need to know, how do I find someone who knows how to do this? Or how do I look and say, did I mention radial integration earlier today? Yeah, I've never seen radial integration before, but oh, here's a really short note on how you do it. Got it. Now I can master that and add that to my skill set. So we often need to look at data the right way. And it is sometimes very easy to mislead people by presenting things in a certain way. Think of the lawyer joke from last time, where you did not lie, but you said things in a very deliberately misleading way. So nature doesn't always give up her secrets easily. And so you need to figure out what's the right data to look at and what's the right way to look at the right data. And that's where logarithms are extremely powerful. It should just be an automatic. It's just, look, let me try logarithms because if it does, I can then send Professor Miller an email and he'll be very happy that it actually worked for something I was doing. I love getting emails like that. I love getting emails from students saying, I tried some extreme cases to just see if something was reasonable. And one of my students years ago said, yeah, we were about to do a big investment. And I was looking at things and the answer didn't seem reasonable. And we were off in one of our equations. We put in a plus sign rather than a minus sign. And it's a good thing it was not nearly as good of an investment as we thought it was. And so when they were trying to just estimate how things were, if you can get these quick estimates, And I will end with, the last line for the semester. You've heard this quote numerous times. If all you have is a hammer, pretty soon every problem looks like a nail. Find things that you're good at, find things that you know how to do, and then try to figure out, how can I take what I'm given and convert that to this?